Bismillahirrahmanirrahim. So today we are going to discuss Poincare Bendixon Theorem. Poincare Bendixon Theorem gives us the conditions for existence of a limit cycle in a second order system. As we know that the limit cycles are the closed orbits within the phase portrait of a second order system, and they indicate existence of an oscillatory phenomena within the system, right? So Poincare Bendixson theorem is one of the theorems that gives us the conditions for existence of limit cycle. It is very easy to understand intuitively. However, it is quite complex when we try to solve it and try to find out the existence of those conditions. So first we state the problem. Let us suppose that we have a system x dot is equal to x f of x. So it is an autonomous system. And we say that if a trajectory of a second order autonomous system remains in a finite region R, then one of the following is true, right? So the trajectories are confined within the region R. These are the trajectories, and these are confined within this region R. Then the trajectory either goes to an equilibrium point, right? So first it could go to an equilibrium point, or the trajectory tends to an asymptotically stable limit cycle, right? So it is telling us that it will either go to an equilibrium point or to an asymptotically stable limit cycle. Not only will it go to a limit cycle, the limit cycle is also going to be stable, which is obvious. If a trajectory has to converge to a limit cycle, it means that the limit cycle is stable. And then finally, the trajectory is itself a limit cycle, in which case there might be a situation that you actually start on the limit cycle, and that is why you remain on the limit cycle for future times. So let's just say that if I start at this point, then I'm going to live on this limit cycle forever. Now there is also an important corollary of this theorem, which says that let us suppose that R contains no equilibrium points, right? Or contains only one equilibrium point, right? So it has either no equilibrium points, or it has one equilibrium point which is an unstable focus or an unstable node. So in that case, and also every trajectory starting in R stays in R for all future time. And finally, it means that in that case, R contains a periodic orbit or limit cycle of the system x dot is equal to f of x. So what we are trying to say is, if you see the above diagram, then let us suppose that this is our point P is our equilibrium point, and it is an unstable equilibrium point, which means that the trajectories diverge from it. Then what will happen is, and the second condition is that all the trajectories that come into R, then they stay in R. So if these two conditions are satisfied, then there is going to be a limit cycle within this region R. So as we have seen, theoretically it is quite easy to understand, and however it is quite difficult to prove, and it needs a great deal of understanding of topology. And and then after that, when we try to apply this theorem, it is quite difficult to obtain a confined region R in which the trajectories are going to get trapped. So we see an example of such a system which has a limit cycle, because we physically know the phenomena, and try to find out the region R in which the trajectories are going to be trapped. And then in the next part of this video, we are going to see an easier way of defining this region R. Okay, so the example we are going to consider is that of glycolysis. Right? So glycolysis is a biochemical process through which the living cells obtain energy by breaking down sugar. Right? So in intact yeast cells, as well as in yeast or muscle extracts, glycolysis proceeds in an oscillatory fashion. So what happens is there is an oscillation kind of phenomena, and you know that when in nonlinear systems there is an oscillation, it means there is a limit cycle in the phase portrait of that system. Okay, so what happens is in this oscillatory phenomena is that the concentrations of various intermediates waxing and waning with a period of several minutes, right? So the concentrations of different chemicals, they increase and decrease, and it keeps happening in an oscillatory fashion. So the chemicals involved in the glycolysis process are, let us say that in the straight space form we call one chemical as concentration of one chemical as X, and it is called adenosine diphosphate, ADP. The other chemical that is involved in glycolysis is fructose 6P or F6P. And the system is given as X dot is equal to minus X plus AY plus X square Y. And Y dot is equal to B minus AY minus X square Y, right? So these are the differential equations for this system. As we see that it is a second order system, only A and B are undefined in this, and A and B are actually the kinetic parameters that determine how fast or slow the chemical reaction occurs. So how do we locate the region R? This is the problem, right? So the problem is to locate a region R such that trajectories will be trapped in them. Okay, right. So how do we go about it? So first of all, what we try to do is step one is locate the nullclines. Okay, so what are the nullclines? Let me write it slightly better manner. So nullclines are actually the isoclines at which X dot is equal to 0 and Y dot is equal to 0. So we see that on these lines, what will be dy over dx? It will be infinity, where X dot is equal to 0, and it will be 0 where Y dot is equal to 0. And the point where X dot is equal to Y dot is equal to 0, we know that that point will be the equilibrium point. So what we do is we first try to find out these conditions for which such phenomena occurs. So from the system equations, these are the system equations, so we equate them to 0. and this gives us minus x plus ay plus x square y is equal to 0, which results in y is equal to x over a plus x square, right? So this is the equation for x dot is equal to 0, which essentially means that this is the equation of that line along which the system trajectories are going to have their slope equal to infinity, or which means that they are going to be vertical along this line. And then y dot is equal to 0. This results in v minus ay minus x square y is equal to 0. So now what we get is y is equal to b over a plus x square. So if we try to plot these lines, what is going to happen? So suppose this is the phase portrait of the system. This is x, this is y. Okay, so we see that for a certain value of a and b, so this is your nullcline y is equal to x over a plus x square, right? And if you remember, this was the nullcline along which dy over dx is equal to infinity, which means that the system trajectories are going to be vertical along this line. Okay, so what is the other line? The other line is y is equal to v over a plus x square, right? And okay, so if we plot it, it is going to be obviously it is going to start at b over a for x is equal to 0, right? And then as x is going to increase, this is going to sharply decrease. It is going to be somewhat like this. Right? So okay, so for better visibility, I've plotted these functions in Mathematica, and they're listed over here. So this is the graph for y is equal to b over a plus x square, whereas this is the graph for y is equal to x over a plus x square. Okay, So we have seen that this nullcline results from x dot is equal to 0, which implies that the slope of the trajectory along this line is going to be infinity, which means that the line will be vertical, whereas this nullcline, this results from y dot is equal to 0, and along this trajectory dy over dx is going to be 0, which means that the line along this is going to be horizontal. Okay, so let us try to plot the lines along these. So we see that whenever the trajectory is going to cross this blue line, it is going to be horizontal like this. Right? But an important question over here is whether it is going to be pointing towards the right or it is going to be pointing towards the left. This is yet to be decided, and we are going to see it in a while. Similarly, along this line, the orange line or the second nullcline, the trajectories are going to be vertical. So whether they are going to be pointing upwards or downwards, this we are going to decide right now. And the crossing point of these lines, where these both nullclines are crossing, it means that this is the point where x dot is equal to 0 and y dot is also equal to 0, right? So this is the equilibrium point of this system. So we see that this system has one equilibrium point. So we will have to prove two things. First, we will have to find out that there is an enclosed region R, and second, we will have to prove that the equilibrium point within R is an unstable equilibrium point. And in that case, we will then be able to find out that a limit cycle actually exists within this system. Okay, so we rub all of this so that we can continue with our further analysis. Okay. Now what we try to do is we try to find out the directions of the flow along these lines, whether it is towards the right or left, or it is towards up or down. And that is going to be determined from the signs of x dot and y dot, right? So the direction of arrows is given by signs of x dot and y dot. Okay. So first of all, let us consider this top region, right? What is happening over here? Okay, so let us start considering few regions. Let us see first the equations of x dot and y dot again, and they're going to help us to solve this problem. So this is x dot. Let us suppose that x dot is greater than 0, which implies that this equation is greater than 0, and that would mean so you have x dot greater than 0 for y greater than x over a plus x square. And similarly, you have x dot less than 0 for y less than x over a plus x square. Okay, so what is the line y is equal to x over x plus x square? So this line was this orange line y is equal to x over a plus x square. So this means that above this line, which is this region essentially, all of this, in this region, x dot is going to be greater than 0, right? As pointed out over here, x dot is going to be greater than here, 0 in this region, right? So we write x dot is greater than 0. And in the region below this line, x dot is going to be less than 0. Okay, so we rub off the rest of the details to work out the sign of y dot. Now, what about y dot? So y dot equation was given as b minus ay minus x square y. And you can see that y dot is greater than 0 for y less than b over a plus x square, and y dot is less than 0 for y greater than b over a plus x square. And we know that this line y is equal to b over x square, a plus x square is this line. Y is equal to b over a plus x square, right? So this means that above this line, we are going to have y dot less than 0. So here we are going to have y dot less than 0. And below this line, we are going to have y dot greater than 0. Okay. With this information, now we can draw the vector field and see where the trajectories are going to be pointing. Okay. So we saw that along this line, this blue line, this is the line where y dot was equal to 0 and implied that dy over dx is equal to 0, and that would mean that the trajectories are going to be horizontal. We see that in this region x dot is greater than 0, which means that x is increasing. So exactly on this line, the arrows are going to be pointing towards the right, right? Because y dot is 0, but x dot is greater than 0, like this. But ahead of this region, since y dot is less than 0 and x dot is greater than 0, the arrows are going to be pointing right and down, right? So this is how we are going to be pointing. Okay. So what will happen when we reach this orange line, which is the line for x dot is equal to 0, right? And we know that at x dot is equal to 0, we have dy over dx equal to infinity, which means that the slope of the vector field over here is infinity, and the vectors or the arrows are pointing vertically upwards or vertically downwards. Okay, so we see that in this region x dot is greater than 0, but y dot is less than 0, and exactly on this line x dot is 0 and y dot is less than 0, which means that the arrows are going to be pointing downwards on this line exactly. Okay. So what will happen between these two lines? X dot is less than 0, but on this region y dot is also less than 0. So this means that within this region the arrows are going to be pointing left and down, right? Whereas when they cross this line, they are going to become horizontal, but since x dot is less than 0, they are going to cross it left and horizontal, right? They're going to cross it left and horizontal. And within this region, that is below this blue line and above the horizontal axis, y dot is greater than 0, but x dot is less than 0. So this they are going to be pointing up and left, up and left, right? And in this region, which is above the orange line and below the blue line, right? So I'm talking about this region. Within this region, what is going to happen is we have y dot greater than 0 and x dot also greater than 0. So the arrows are going to start pointing towards right and up, right and up. So we see that we are finding a sort of circulatory or enclosed kind of trajectories actually moving within the system. So if I clean all this mess and make a neat diagram, it is going to be somewhat like this. I'm struggling a bit in making neat arrows. Right? So you see that there is a kind of an oscillatory motion involved within the system, which indicates that there is a limit cycle. There is also an equilibrium point at this, which is the intersection of x dot is equal to 0 and y dot is equal to 0, and it is given as at B right. So I'm not going to prove this, but if we are going to plug in this equilibrium point and we are going to linearize the system about this equilibrium point, then the system trajectories are actually, they point out, or the eigenvalues actually point out that this equilibrium point is an unstable node. And if this is an unstable node, that essentially means that one of the conditions of the Poincare Bendixon theorem is satisfied. It only remains to find out the enclosing region R in which this flow, which is being seen moving in an enclosed fashion, is going to be confined. So until now, we have been able to actually find out that the system flow or the direction of the vector field is in such a fashion that it points out to the existence of a limit cycle, but we have to find out the a trapping region R in which the trajectories are going to be confined. Now, to show this, we have to show that all the vectors on the boundary point into the box, right? We have to make a box and we have to show that all the points move into the box. So it is very easy to draw the vertical and horizontal boundaries. Why? Because we know that along this line, when the trajectories come, along the vertical line, when the trajectories come, they actually start moving towards the right. The arrows start moving, pointing towards the right. So we know that the trajectories are moving inward into this region. And similarly, along the horizontal line, we see that when the trajectories cross this blue line, after that they start moving left and up, right? And because of their fashion of moving in left and up direction, they actually remain confined or they actually remain above this horizontal line. The only problem is to find out a region or the boundary in the top right corner of this diagram. So the claim is that the boundary of this region looks somewhat like this. Okay, so in order to prove this, we see that this blue trajectory, this starts at y is equal to p, right? And exactly above the equilibrium point, this point is given as b comma b over a, and it touches this trajectory y is equal to x over a plus x square somewhere. To show that this diagonal line is actually the line that shows the boundary of the trapping region R, we first have to consider x dot and y dot in a very large x, right? When x approaches to infinity. So when we say that limit x approaches to infinity, then right. So when this is the x is very large, we know that this minus x term and a by term, these both are going to get ignored, and this is going to be almost equal to x square over x square y. And similarly, y dot will be almost equal to minus x square y. Okay. So when x is very large, we try to calculate the slope of the trajectory there, which is dy over dx, and it is given as y dot over x dot. This is given as minus x square y divided by x square y, which is minus 1. So we are clear that for very large x, the system trajectories are going to be roughly parallel to this line, which has a slope of minus 1, right? So this is a line which is, for which we have drawn m is equal to minus 1. Okay, the slope is minus 1. Now it only remains to show that just like we showed that the arrows are going to be pointing left and upward or right and upward or right and downward, similarly we have to show that the trajectories actually remain confined within this line. Okay, and for that we have to consider the signs of x dot and y dot for very large x. Okay, so how do we do that? So what we are doing over here is we're going to calculate let us just consider x dot minus y dot, right? And this is given as minus x plus ay plus x square y plus b minus ay minus x square y, and if you do the simplification, it is simply going to be equal to b minus x, right? So let us suppose that this quantity is greater than 0. Why we are doing this? We are going to see this. If this is greater than 0, this implies two things. This is greater than 0. Okay, so we are going to consider here the case when b minus x is less than 0, which implies that x is greater than b. What will be the condition on x dot and y dot in that case? X dot minus y dot is less than 0, which means that minus y dot is actually greater than x dot when x is greater than b. So we have reached this point that minus y dot is greater than x dot when x is greater than b, and if we try to calculate the system trajectories slope at this point, then we have minus dy over dx is greater than 1, which implies that dy over dx is less than minus 1, right? So in the first part, when we considered very large x and for that we considered y dot and x dot, we were able to find that actually the system trajectories are going to have a slope equal to minus 1, right? But for sufficiently large x, when we consider x dot minus y dot, we found that the system trajectories are going to have a slope which is going to be even lesser than minus 1, right? So it means that the trajectories are going to be pointing inwards here, right? When they cross this line, they are going to be, along this line, they are going to be minus 1. But within this region, they are going to be pointing inwards. Okay, so now we have actually found out that the trajectories are trapped within this dotted red region. And this is the region R in which the trajectories remain confined. We also commented that the equilibrium point b comma b over a plus b squared can be used to check that the linear system eigenvalues at this point are actually unstable. If they are unstable, it means that we have a trapping region R, right? We have a region R. The equilibrium point x star is unstable. So all the conditions for existence of a limit cycle are satisfied, and which means that the limit cycle exists within this region R. Thank you.